Hi everyone, and welcome to another mini course at Physics Latam. Today we have Professor Son Sun from IASM, Zhejiang University, with a mini course on geometry of Einstein metric. Professor Son Sun's research focused on differential geometry, complex geometry, and geometric analysis. He received the Sloan Research Fellowship in 2014, the Oswald Level Prize in Geometry in 2019, and the New Horizon in Mathematics Prize by the Breakthrough Prize in 2021. Before he joined IASM, he was professor at the University of California, Berkeley. Please remember to raise your hand at any point if you have any question, and I will leave you with some. Please go ahead.
Okay. Yeah. Thank you. Thanks, Daniel, for inviting me to give this series of lectures. So I will talk about the geometry of Einstein metrics. So maybe Einstein metrics. So by the way, I'm not very confident about this connection, Zoom connection. So if at any time you have trouble hearing me or viewing the writing, please let me know. So I mean, this is for I suppose for physics. So we know that in general relativity, we have the Einstein equation, which is the equation that governing the spacetime. The spacetime is defined by a Lorentzian metric G. We have the Einstein equation. It's Lorentzian. The G mu plus lambda G mu kappa T mu. So this Einstein tensor G. And then I suppose everyone knows this. But for our purpose, in these lectures, we will talk about the remaining counterpart. Which concerns a Riemannian metric G. G now is a Riemannian metric, is positive definite at every point, and we will concern. I mean, for general, in spacetime, in general relativity, we have a matter, have a stress energy tensor. Here, in Riemannian geometry, we only care about most care about vacuum spacetime, vacuum space. So it's just let's write Ricci equals lambda G. So Ricci is a Ricci tensor. I will explain a bit more just a few minutes. So this lambda the Einstein constant, cosmological constant. So I mean here this in the original Einstein equation is Einstein tensor is defined as Ricci minus scale curvature over 2 times G. So essentially it's essentially equivalent to saying that this Einstein tensor is proportional to G. I mean, if the dimension is at least 3. So why do we care about this? I mean, from the geometric viewpoint, this is important equation. In geometry, it represents just optimal shapes in geometry. One type of optimal shapes. We will get back to this later. So it satisfies a important equation. And then it does not have maybe I should not. This is strange. If I enlarge, then I have to scroll. Anyway, let's do this. It does not have immediate physics meaning, but they have also these objects have important play important role in physics. First, they they play a role in so-called Euclidean gravity. Some of this can view this as a weak rotation of the solutions to the space-time in general relativity. It's also useful this is analytic continuation approach, and it's useful in computing some integrals, path integrals via analytic continuation. So that's it. That's important. And another thing is that they appear in high dimensional gravity theory, where you have the space-time, 4-dimensional space-time, but you also have the extra internal dimensions where the signature is Riemannian, and you ask them to satisfy the Einstein equation, then you meet this Einstein matrix. For example, if you have a Riemannian Einstein matrix in dimension n, you can view it as a static solution to the Lorentz Einstein equation in dimension n+1 just by adding a trivial time direction with a negative signature. Anyway, so these are just say why people care about this. So let's to do mathematics. We have to understand this equation in a little bit more detail. So the first thing is it's about Ricci curvature. Let's recall the notion of Ricci curvature or in general curvature. So if you have a Riemannian manifold, usually we denote by M with dimension is little m, and this Riemannian manifold, Riemannian metric. And we pick a point P in M. Then the curvature at P can be understood as the obstruction to make this G standard in the neighborhood of P. So if this G, if you can choose correct coordinates, you can choose suitable coordinates so that this G becomes the standard Euclidean metric near P, then there's no curvature. But you have a curvature. So mathematically, so we know that in the geodesic normal coordinates centered at P, this just means it's a coordinate induced by the exponential map in a neighborhood of 0. So you use the coordinate on the tangent space. So let's denote this by x1 to xm. Then we have a expansion. This tensor Gij at 0. So it's the first term is delta ij, and then there's no first order term. It's essentially the fundamental theorem of Riemannian geometry. And then the second order term is quadratic in xi's. So you can write as sum over kl, some xk, xl, and the coordinate, the coefficient is I k jl. And then third order term. So the second order term this appears. This is exactly the curvature tensor, the components of the curvature tensor at P. So there's curvature tensor in this coordinate. And if you take the volume density of this metric, so it's square root determinant of Gij. Sometimes just write as square root of G. This is simple computation. If you take the determinant to the linear first order, it just becomes a trace. If you take the trace of this, you get something. So Rij xk xl. Okay. And this rij, they are components. Maybe let me not scroll. So these are components of Ricci tensor. So Ricci is rij dxi tensor dxj. J. Sorry, this coefficient is 1/6 square root here. So you see that the geometrically the Ricci curvature tensor controls the second order expansion of the volume density, and then there's a further curvature, scalar curvature, is defined as this is a function scalar. If you integrate this volume density, you get the volume. So volume of a ball of radius r in the metric G, and then you can compare this with the volume of a standard ball inside the Euclidean space dimension M. Then what we get is 1 minus the scalar curvature at P, right, R P over 6m plus 2 R squared cubed. You notice that this scalar curvature, the sign of the scalar curvature at P, controls the infinitesimal the comparison between the volume of a ball of radius r and standard ball inside the Euclidean space. If the scalar curvature is positive at P, then the volume is smaller for r small, and when scalar curvature is negative, then the volume is bigger. So this is scalar curvature. Scalar curvature controls volume in small scale. And the Ricci curvature controls the volume density. But one important fact is that actually the Ricci curvature can control the volume in large scale. So that's the content of comparison geometry. Let's compare Ricci curvature. This is important. So, and it only works in one way. So if the Ricci curvature of G is bigger or equal than m minus 1 times k, where k is constant. So what does this mean? This means normally you write this way, but it really means that the Ricci tensor minus the m minus 1 k times G. So this is a symmetric two tensor is non-negative definite. At every point, the corresponding matrix as a symmetric matrix is non-negative definite. Then we have Bishop inequality. If you learn GR, this is essentially there's a similar thing called Fernando Riccioturi equation. So it's similar to that. Basically, you take a so suppose you're within cut locus. So suppose you have a geodesic. So you have a region where this expansion map is a diffeomorphism from P from this onto this ball. Then if you can take a geodesic polar coordinate. Geodesic polar coordinate. 所以我在上课。好的，好的。So take the radial coordinate r and the spherical theta. So the point here is that you have this coordinates along this minimizing geodesic within the cut locus, but this works not, you don't need to require r to be small. So we can write this d mu, which is the volume form of G. At some function f r theta times dr, the standard. This is a standard volume form on the round sphere. So basically, you compare your volume form with, if you just take dr times this is just the standard volume form of the Euclidean space in polar coordinates. And then what Bishop inequality says that if you fix theta, this function f r theta, divide by some standard function f r is a decreasing function in r. You don't require r, you don't need r to be small, so r is 0, it's equal to infinity. So if you are a compact manifold, then you know that at some point you must hit a conjugate point. Then you must hit a cut point. Then the d mu will be 0. So this f r theta will be 0, so it will become 0. So what is FR? FR is, let me just write here. This is a standard form. It's the corresponding function, this capital F in the model space of constant curvature. When k equals 0, it's flat, it's r to the n minus 1, and k is positive. That's a sine square root k r over square root k n minus 1. Maybe it's too thick. Let's change it to a thinner one. Is it better this way? Okay. So, and then if k is negative, sine h negative k r over square root of k to the n minus 1. So essentially, it's, you use some kind of Riccati equation similar to what I said about similar equations in relativity. You get this monotonicity, this inequality, and if you integrate this inequality, what we get is so-called Bishop-Gromov inequality. Right, integrating this. Bishop-Gromov volume inequality. The control volume in large scale is that if you have, say, Mg is a complete Riemannian manifold, it's complete. I suppose everyone taken Riemannian geometry course. So complete means that geodesic can extend forever. This is an important notion in Riemannian geometry. In the Lorentzian geometry, it's slightly more complicated. So then the volume of a ball of radius r center to P divided by the volume of a corresponding ball BR inside MK. This is the the model space of constant curvature, constant sectional curvature K. So when K is 0, it's just flat space. When K is negative, it's hyperbolic space. K is positive, it's a sphere. This is increasing R0. Okay, so reach under this condition. So this is important. So the difference, I mean, if you take K equals 0, so we know that you can do using the local expansion unit scalar curve to control it. But now the key point here is that this works for all R. This is a large geometry, and it only works under the assumption that the Ricci curvature is bounded below by this. It does not work if you just have a scalar curvature bounded below. It also does not work if your Ricci curvature is bounded above and you want to reverse the inequality. That also does not work. It's very special. So consequence of this is a Miles theorem. Miles theorem. That if your K is positive, then the diameter of mg is bounded by pi over square root of K. There's another consequence. Let's say another consequence. It's from the Bishop inequality. It's because, as I said, so when K is positive, this special function is already 0. So on a sphere, you know that the diameter is bounded is a finite. So you compare with a sphere, you get this. So this is the meaning of Ricci curvature. So the upper is Ricci related Ricci lower bound. The volume comparison. We'll talk about the infinitesimally is related to expansion in the volume density. Globally, the lower bound is related to volume comparison with models, but also in terms of analysis, analytically, so this Ricci curvature appears in the Bochner-Weidenburg type formula through commuting derivatives. We know that curvature is what appears when you commute derivatives on a manifold. Here, Ricci curvature also appears here. So if M is compact, so if you have one form alpha, then you have a Hodge Laplacian, which is d star plus d star d alpha, and you also have it's called rough Laplacian. It's Hodge Laplacian operator. This is a Laplace star, Laplace alpha. It's a rough Laplacian. So the Laplace you've used as a map from omega 1 to omega 1 tensor omega 1 to alpha to Laplace alpha. Okay, you have fit in a tangent vector, you still get one form. So then Laplace star is a formal adjoint of this operator. So this is both operators are non-negative. So and then there's a formula relating them. The difference is Ricci alpha. So Ricci as a symmetric 2 tensor, it can be viewed as a symmetric endomorphism from omega 1 to omega 1. So in local coordinates, it's Ricci alpha equal Rij alpha k g jk sigma jk dxi. So if alpha equals alpha I dxi. So we often like you interchange. So because you have a Riemann matrix, the tangent bundle and the cotangent bundle are naturally identified. So the Ricci is the 2 tensor. In so you can view it as a bilinear form on the tangent bundle, but it can also be viewed as a endomorphism of the tangent bundle or endomorphism of the cotangent bundle by this identification. So if M is compact, then if Ricci is say positive, non-negative, you see by integration. So if you have harmonic one form, if Laplace H alpha equals 0, then implies that Laplace alpha plus Ricci alpha is 0. But then you can take inner product with alpha, you integrate on M. Then you see that Laplace alpha squared plus Ricci alpha equals 0. So this implies that Laplace alpha has to be identically 0. So harmonic one form has to be parallel. And if Ricci is positive at one point, then this term integral is already positive if alpha is not 0. So the consequence is that if Ricci, maybe here just the Ricci non-negative, parallel one forms is a linear vector space with dimension at most the dimension of M, because it is determined by its value at one point. The evaluation map. So at one point, this is the injective map. So the dimension is at most M. And then the kernel, the space of the dimension of the space of harmonic one forms is by Hodge theorem. The dimension of H1 R is less or equal than M. So, but if a Ricci curvature is positive, it implies H1 is 0. So this is control of Ricci curvature. This again, the non-negativity, the lower bound of Ricci curvature controls topology, first Betti number. So maybe you have seen that the lower bound of Ricci curvature, the positivity of the Ricci curvature is important. And what about the upper bound? We said that there's no volume control with the upper bound of Ricci curvature. So because we are interested in Einstein metrics, right? Einstein metric is the Ricci curvature is proportional to the metric sense. So it automatically has a lower bound, but it also has an upper bound. And this upper bound, there's not much you can say, but there's one thing one can say is that the Ricci, this Ricci non-active, Ricci non-positive as a tensor, this controls symmetry in the following sense. When the curvature is negative, you tend to not have symmetry. So again, we work with MG compact. And here is that there's another Bochner formula that's probably not as famous, as well known as that original one. So if you take one form alpha, instead of taking its Hodge Laplacian, one can take a we defined S alpha S alpha is to be the symmetrization of Laplace alpha. What does it mean? So this S alpha is so this will be element in sim 2 of omega 1. This is contained in omega 1 tensor omega 1. So it's symmetric. So it's Sij. It's a 2 tensor. It's Laplace I alpha j. So this Laplace alpha is an element in omega 1 times the tensor omega 1. It's not symmetrical. It's symmetrized. Laplace j alpha I divided by 2. Okay. So this is the operator. So the important thing that this S alpha equals 0 if and only if the alpha sharp, it's a corresponding vector field, dual vector field of alpha is a Kenyon vector field. Kenyon field. It's symmetry. It's a symmetry of the metric, i.e., the derivative is 0. Okay, so this is the equation satisfied by a dual one form of Kenyon vector field. And also we know that the trace of S is just a sum of I, Laplace I, alpha I. This is a it's divergence, negative divergence of alpha. So it's it's 0 if and only if the vector field alpha sharp is it preserves the volume, so volume preserving. And then one can similarly have a Born formula. You can compute S star S alpha. Okay, the one has to get. I mean, it's a not difficult computation of commuting derivatives. I think I get the coefficient correct. It's also Laplace star Laplace alpha. But here you get the negative sign, reach alpha, and then you have extra term which is Laplace of trace S alpha. Okay, so this is so this trace is a function. Take a Laplace, it's still a one form. Maybe just let's say D one form. So now if it's compact and reach is non-positive, this similar as before. If you have any kernel of S alpha, if S alpha equals 0, then of course then the trace of S alpha is also 0. So you do an integration by parts, you see that Laplace alpha equals 0. So the alpha again is parallel. So the vector field, dual vector field is also parallel. So it means the dimension of Kenyon fields as alpha equals 0 is at most m. And if we, what other color is good? Do yellow. Is this feasible? Yellow color. Okay, good. If it reaches negative, then this will be 0. So there's no Kenyon vector field when the reach curvature is negative. So this is what I mean by the negative Ricci curvature controls symmetry. So so returning to, I mean, our main topic is Einstein metric. So Einstein metric is the equation that Ricci is proportional to G. So I want to recall this facts for the Ricci curvature. So how we understand the Ricci curvature. Okay. Now let's go back to the Einstein equation, the Einstein metric. Rich equals lambda G. So this is so the in general relativity there are two ways to derive the Einstein equation. One is from the Einstein's original equivalence principle. The other one uses Hilbert's Einstein-Hilbert function. Is a very variational approach on Lagrange formalism. So here I mean, of course, the second one it's easy to extend to the Riemannian setting. So we consider the Einstein-Hilbert functional. So the Einstein metrics, they are critical points of Einstein-Hilbert functional. So it's EH Einstein-Hilbert G. So it's just it's an action. Sometimes I write S, sometimes I write R. So it's just for scalar curvature in mu G. This is the very natural action. In the Lorentz setting, you must have seen this already. But anyway, this is basically the same computation as the variation of this Einstein-Hilbert function along the Riemannian metric is given by the inner product of Ricci minus R over 2G and delta G. So in particular, this is 0. G is a critical point. Say the Euler-Lagrange equation, if and only if Ricci minus R over 2G equals 0, and when n equals, if you take a trace of this, when m is bigger than 2, this is equivalent to that the Ricci has to be 0. Of course, when m equals 2, this is automatically true. And that's not surprising. So this does not say anything because when m equals 2, we have Gauss-Bonnet theorem. On a compact map, this is a constant. Does not depend on the choice of metric. So this means the Ricci-Ferrat metric and the Ricci curve equals 0. They are the critical points of the Einstein-Hilbert functional. M equals 2 and m bigger than 2. And more generally, for general Einstein metric, we need to consider normalized Einstein-Hilbert functional. This is EHG equals you restrict. So this is like the Lagrangian multiplier or whatever. You minimizing this over a smaller set. You fix the volume to be 1, and then the equation becomes more general. It's exactly the Ricci. You allow it to be proportional to the matrix, and or you can consider all Riemannian matrices, but just you make a normal you divide by the volume. The volume and m minus 2 over m. So that if you rescale the metric, if you multiply G by a constant, this function is invariant. And then this critical point, maybe the critical point, when m bigger than 2 satisfies the equation that Ricci equals lambda G for some lambda. Okay. So this is a variational characterization of Einstein metrics. We will not talk too much about it because this is physics lesson. We do about the analysis, but we want to at least mention one thing, that the PDE viewpoint, the Einstein metric satisfy nice equation, which allows some theory to be developed. So the main point is that we can, I mean, you have also similar thing in relativity. If you choose local or harmonic coordinates, so the coordinate itself are harmonic functions with respect to g, and then the Einstein equation becomes the equation that 1/2 Laplacian 0 of Gij plus q t partial t equals lambda Gij. So this Laplacian 0 is just a standard Laplacian, which is sum I and partial squared. And this q is a quadratic in terms of partial g. But the main point is that from a PDE viewpoint, this second order term is here. It's essentially the Laplacian equation acting on this matrix. Each component is a non-linear for the elliptic PDE system. So elliptic means essentially it's a perturbation of the Laplacian operator in to a nonlinear equation. So this is very different from the Lorentzian setting on GR, where you instead of Laplacian you get the wave operator, which is much more difficult from the PDE viewpoint. For example, this ellipticity implies, I mean, it's not automatic, but one can do work to show that an Einstein metric is real analytic. Namely, you can choose coordinates so that the components of the metric it becomes real analytic functions. This is rarely the case in GR. This is one thing. The other thing is that this Einstein equation asks Ricci to be constant. So why not if we take a scalar curvature equals constant? Ricci, we have Ricci equals constant, or we can take the sectional curvature to be constant. So this is elliptic. This is I mean, in correct gauge you get elliptic PDE, but then and it means that the number. So the naively heuristic speaking is the number of unknowns. Essentially equals the number of constraints. The degree of freedom of unknowns is a Riemannian metric. It's a symmetric 2x2 matrix, m by m matrix at each point. And the Ricci tensor is also symmetric tensor at each point. But if you just ask for scalar curvature to be constant, then the Riemannian matrix is a big matrix, and this is just a function. So this becomes a so-called a underdetermined system. So you have too many freedoms. And then if you ask sectional curvature, this will be overdetermined. So this Einstein equation, they are right in the middle, which is allows some flexibility and rigidity. So we will now explain a little bit more. But so this is a PDE viewpoint, and then the main question I believe in this area, in my opinion, is first to construct Einstein matrix. Just construct this optimal structures. The optimal in the sense that it's the critical points of the Einstein hyperfunctional the existence construction. Right. So this will require solve PDE. It's difficult PDE in general. And because we study Riemann matrix, we want the matrix to be complete at least, or compact. Let's ask more restrictive solutions. Matrix. So there is, for example, which manifold admits solutions, right? So this, so we will explain. There will be a relation with topology, and then sometimes you don't get just one solution; you get many solutions, and then you want the classification. Sometimes called moduli, or if in some cases you can prove uniqueness. So this is you want to understand all the solutions. For example, on a manifold, or on a fixed manifold, or under some constraint. So these are the main questions. There are many results known, but there are also many questions unknown. So we will go first. Consider the low dimensional case. So when m equals 2. This is so here the Einstein being Einstein matrix same as matrix with constant Gaussian curvature. Same as because in dimension 2 there's only one curvature, which is the Gaussian curvature. So everything is same. Gaussian curvature. And then this is this question is essentially 19th century mathematics uniformization theorem of surfaces. So for simplicity, we let's consider oriented closed surface. So any oriented closed surface admits a Einstein metric. And if we want to actually more precisely, so it's a unique in each conformal class. So let's explain what is this unique and conformal class. So if you fix arbitrary Riemann metric, then it may not be Einstein, and then conformal means I just multiply by something like e to 2 phi times g. So this new metric differs by the original metric just by a conformal factor. So it preserves the angle. So if you fix g, then in this conformal class of all function phi, then there's a unique one, but it's up to conformal transformation. So the unique up to conformal transformation. And let me not say this. Just say that we have we know what these are, right? So these surfaces are. So I say so. So the first case is when genus is equal 0, then of course you have a round metric. That's 2. But then you have a scaling, right? But not just scaling, but if you turn in terms of this metric tensor, there's a Mobius transformation, so it's unique. up to scaling. But also, there's a PGL2C action. So you identify S2 with CP1. Then we have the Mobius transformation on the S2. It is conformal. It preserves the conformal class. So if you take the round metric, you pull back by elements in this PGL2, then you will get a new metric. It is still in the same conformal class, and they still have constant curvature. So this is a little bit more subtle here. But now when genus equals 1, and then the metric is flat, so we have the torus. Just take the rectangle parallelogram. Better take. Identify the opposite sides. So there's a flat. And here the metric is unique up to scaling. So different parallelogram, they may have different conformal class, but if you fix the conformal class, unique, and genus bigger than 1, so then this is constant curvature. Let's say reach equals lambda g is lambda positive. This is lambda equals 0, lambda negative. This is hyperbolic metric. It's also unique up to scaling. And these objects can be formed from it takes some polygon in the hyperbolic disk, and then you identify them suitably. So here, this is an octagon, so you get a genus 2. And we have Gauss-Bonnet. Tells that the R d mu g equals 2 pi chi m, right? So if R is constant, this chi is just the constant times the volume. So the sign of this lambda is same sign as the Euler number. So this matrix, I said each conformal class is unique, but when the conformal class varies, then you will get a moduli, and we have a good understanding of this moduli spaces, the space of all solutions, and it's related to modular curve, Teichmüller space. Anyway, let me see. So maybe it's better to just see that uniqueness is quite easy to see when the genus is at least 1. The point is, let's just write down the equation. It's just a little bit more explicit. So you have a G, it's a Gaussian curvature, Kg. This may not be a constant in general, and then if you take e to the 2 phi g, the Gauss curvature, e to 2 phi g is e to negative 2 phi, negative phi plus kg. It's a computation. So if you want this to be a constant, so want this k e to 2 phi g equals constant, and this constant is determined by if you fix the volume, it's a constant anyway. So the constant has to satisfy the constraint that k to 2 phi the d mu g. Gauss-Bonnet. Okay. So the point is you want to solve this equation. You move this e to 2 phi, that's negative phi plus kg equals e to 2 phi times k bar. You want to solve for phi, right? And then the claim says this equation is always solvable. For this, if k bar satisfies this constraint, and it's unique. So let's say uniqueness. What does it mean, right? So let's for simply let's just consider the case g equals 0. Then if g is 0, chi genus is sorry, this now there's a conflict of rotation. This maybe that's not right. G is right. The Euler number. The G is Riemannian metric, not genus. Euler number equals 2 equals 0. Smaller than 0. Okay. There's a to avoid the conflict with the metric G. So if your Euler number equals 0, okay, then if you have a true, if both G and e to 2 phi G constant Gaussian curvature, it means it's that they both have to be flat. So that means kg equals 0, k bar is 0. What do you get? You just minus Laplacian phi equals 0. Then, right, this term is 0, this term is 0. So that means its compact phi has to be constant. That means your metric G, the two metric differ just by a rescaling. Okay, this is when chi is 0. When chi is negative, it's also not very difficult. This with we use so-called maximum principle. It's constant Gaussian curvature. So by a rescaling, we may assume that they're both equal to, let's say, both equal to -1. Okay, just rescale them. We allow rescaling. Then what we get is minus Laplacian phi minus 1 equals e to the minus e to 2 phi. Sense? So this, if you just integrate this, you don't get a contradiction. You just get e to the negative 2 phi, e to the negative phi integral equals 1. Doesn't give you much information. Instead, what we can do is that we look at the maximum of phi at say p. Let's suppose p, realize phi p is the maximum of phi. Okay. At this point, so we know that in Rn, if you have a function which has a maximum at one point, then the first derivative has to be 0, and then the Hessian has to be non-positive, right? And this Laplacian is the trace of Hessian, so it means negative Laplacian at this p. This has to be non. is maximum is non-negative. So that means so you write e to the negative 2 phi equals 1 plus apart from phi. So this is smaller than 1, right? At this point, we will have this. This implies that at this point, phi has to be non-positive. Make sense? So this implies the maximum of phi is non-positive, and similarly, the minimum of phi has to be non-negative using similar argument. So that means the phi has to be 0. This is the proof that if the Euler number is negative, then there's a the constant Gaussian curvature metric in the conformal class has to be differ just by a scaling. So this is important technique. Anyway, but here is very simple. But then this is left with chi positive in the case of S2, and then obviously you cannot prove phi equals 0 because you know there's this component, and that's much more complicated. And then the main point is here is this sign here is important, right? If instead of so if you get in the case when in the case of S2, you will do this, you will not get the maximum phi non-positive. You will get maximum phi non-negative and minimum phi and non-positive, and that does not tell you anything. So this is the upshot that in dimension 2, Einstein metrics are pretty well understood. Even though there's still, I mean, you can still ask much more refined questions, but for the main purpose of understanding the construction and the classification of Einstein metrics, that's well known. Now let's move on to dimension 3. So here, okay, so we talked about the case of surface. Now let's move on to dimension 3. So here is a fact that Einstein metrics also have a constant sectional curvature. So similar as so the constant sectional curvature spaces, they are classified either spherical, sphere, Euclidean, or hyperbolic constant curvature. So these spaces are, so that means locally it's just a piece of one of these model spaces up to scaling. So it's kind of rigid piece in locally. However, the difference from two-dimensional cases is not every string manifold. Let's say oriented closed string manifold admits a Einstein metric. And the topology is more complicated, right? For example, if you just take M equals S1 times S2, so it's a simple one. So S1 is flat, S2 is round. It has positive round metric, positive curve. But the product does not admit an Einstein metric. This is because, so if it has admits an Einstein metric, it will imply the universal cover has to be the standard space. Right? So it has to be diffeomorphic to either 3 sphere or R3, because hyperbolic ball is also diffeomorphic to R3. But this one has universal cover R times S2. It's not the standard one, so it cannot admit an Einstein metric. So that's it. This topology in three-dimensional is more complicated. You cannot just use Einstein metric to uniformize them. And if every streamer will admit Einstein metric, then the things will be much too simple. So for example, we have a Poincare conjecture. We all know. It says that if pi1 m equals 0, then m is it's a homeomorphic or diffeomorphic to S3, right? So if you have Einstein metric on them on m, then of course m has to be the 3 sphere. But we don't know if you can find Einstein metric. So you want to find Einstein metric, and then this motivates the Hamilton in 1982 introduced a notion of Ricci flow. It's a technique of Ricci flow. So if you start with any initial metric G0, you try to deform G along the negative Ricci of G. And then if you can find a fixed point of this flow in the end, then you will see a Einstein metric, and then if everything worked well, you will prove the Poincare conjecture this way. However, it's known that the Ricci flow in three-dimensional almost always encounters singularities. Singularities unavoidable. And one needs to do surgery to understand this singularity and the surgery. To when you have a singularity, you want to cut this into pieces, and then you flow them into a surgery, and then you flow them in. Okay. Yeah. So I will talk about this Ricci flow. One has to encounter its singularity, and then one has to do surgery, and then it was proved by Perelman using Ricci flow with surgery. So Perelman does not only prove the Poincare conjecture, but also prove so-called geometrization conjecture. Now we have the geometrization theorem. It is a three-dimensional analog of the uniformization theorem. We cannot uniformize with constant curvature, but we can allow more general pieces. So M3 manifold closed oriented 3 manifold. So it can be cut along surfaces, some surfaces, into pieces, open pieces. Each of them admit one of the 8 model geometries. This was started from Thurston geometrization conjecture. So this among 8 of them, the 3 of them among these 8, the 3 of them are the Einstein was spheres, Euclidean, hyperbolic 3 space. But then there are also S2 times R, hyperbolic times R, S2 R tilde. I mean, this is just names. You don't really need to understand it. But I just want to say that this S2 times R is just product of the two sphere times R. So this is not Einstein, but it's still a homogeneous space. So all these are homogeneous geometries. So this S2 times S1 is actually S2 is one of these model geometries, but then there are more complicated ones. So this has to do with the fact that three manifold topology is much more complicated than two manifold surfaces. But in terms of Einstein metrics, I think because we have this big results, we can understand them. Now, if we move on to dimension at least 4, the Einstein metrics, they are not locally rigid pieces, not necessarily constant curvature, sectional curvature. So means it's really a solution to some PDE. It's not. It's in general. It's more flexible. There's a flexibility. Because if it's constant curvature, locally it has to be exactly one of the three, right? So it's too rigid. However, if the dimension is too large, then you also don't have much control of this Einstein matrix. Namely, like what does the existence of Einstein matrix say about the space? So when M is at least 5, so currently there's no known topological obstruction for a manifold to be admit Einstein matrix, and the PDE too complicated in general. Okay, if you don't put extra structure in it, then for example, even on spheres, high dimensional spheres, there could be many Einstein matrices. So this on the one hand, you don't know what is obstructing them, but it's on the other hand, it's also difficult to construct solutions. So this is this is difficult in dimension at least 5, and it's probably difficult to imagine this Einstein matrix have interactions with topology in high dimensions. So what are the interesting cases? And of current research is first one is when M equals 4. It's like a Goldilocks zone. It's not flexible, but it's not too flexible, right? So one thing is because of relativity is 4 dimensions. So there are interactions with the general relativity very naturally, but also it has with topology. So there are obstructions. We will get to this later, and also even smooth topology. So we know that in 4 dimension, the distinction between topology and the smooth topology, to this Donaldson's theory, gauge theory. But the Einstein metrics, they satisfy partial differential equation. To make sense of this equation, you need smooth structure. So it's also the relation with smooth topology, interaction, Cyber-Witten equation, etc. We will not talk about much about this, but just quote the result of LeBron. If you're interested, you can read by yourself. There's a lot of results. For example, he can find a manifold, the two manifold, M1 and M2. They are homeomorphic for manifold. but one of them admit Einstein. The other one no Einstein. So that means, I mean, of course, it's not a consequence of. They have to be smoothly non-diffeomorphic. But it's not the Einstein pattern not used to distinguish them, but actually as a result, so you know a priori they are different, and then you know that one of them has Einstein, the other one has no Einstein. So it's interesting, and this uses Cyber-Witten invariant. We will talk about the constructions of the interesting local constructions, complete and also complete matrix in 4 dimensions. There are many constructions, so it's an interesting topic. The other one is in high dimensions, general dimensions. If we do not consider the very general Einstein metric, but with if we consider Einstein metric with extra structures, or a special class of Einstein metrics, then there are also many study and very interesting. And especially this extra means that the interactions with connections with special number systems, so like complex numbers, quaternions, octillions. So complex geometry will play an important role here. And to study Einstein metrics on a Kähler manifold, so Kähler Einstein. I think now it's good. So we will let's first talk about this second. So the rest of these lectures will mainly focus on these 2 cases, and I think next let's discuss is what do we mean by extra structures. So this touches upon another important topic in Riemannian geometry, the holonomy group. So this is a algebraic invariant of a Riemannian manifold. If you take, say, MG, let's say complete Riemannian manifold. Then we will get a group out of this. And what we do, so suppose this is my M, I take a point P. If you take a loop, the gamma is a P is in M, gamma is a piecewise smooth loop based at P. Let's just say it's smooth. Okay. Then if you're given a tangent vector at P, I can parallel transport it along gamma, and when I get back to P, it may not be the same vector, and then this is a holonomy. So there's a gamma induces a parallel transport. There's a TPM to TPM parallel transport. So this is a isometry. And for simplicity, let's assume this gamma is contractible. So then this P gamma will be isotopic to identity. So P gamma is an element in SO of TPM. And if we identify TPM with some RM, and this is SO of M, using this is isometric identification. So in other words, this P gamma is an element in SOM. It's not well defined, but it is defined up to anyway. For one gamma, that's not matter much. But if you consider the set of all gamma, all such gamma, this forms a group because you can compose the parallel transport along two loops. Just by compose the two loops, you get a new piecewise smooth loop, and there's the inverse, just going backwards. So this is a group, and this is called holonomy group, and holonomy MGP depends on all this. So it's a restricted holonomy, meaning that we only consider contractible loops. So this is a connected group, subgroup of SOTPM. So if we identify with this with SOM, so this group as an abstract group, a subgroup of SOM is not well defined, but it's a conjugacy class is well defined, and because it also depends on the choice of P. But if you change the point Q, then the two holonomy groups will naturally be conjugate to each other. That's just by choosing a path connecting P and Q, then every loop based on P will give you a loop based on Q. And then the corresponding parallel transport is conjugate by the parallel transport along from P to Q. Anyway, so and it is a theorem that this is a closed subgroup, is a Lie group. Lie subgroup. So this is so if you start with any complete Riemannian manifold, we will get a group. Okay, and then it's a question like can we use this group to understand the metric? What does this group reflect? What information does it reflect on the metric? And then the first thing is that this structure, this group, if you take the non-commutativity here is really related to the non-commutative of parallel transport, right? If you take a parallel transport gamma and then you take a gamma prime, or you first do along gamma prime then gamma, then they are normally different, non-commutative. And then, but there's parallel transport. If you know the geometric understanding of curvature, that's exactly curvature. So we have the Ambrose-Singer theorem. So this Lie algebra of this. That's just denoted by the it's exactly generated by curvature. So what is this? This is in little SOM. Little SO of TPM. There's a skew symmetric endomorphism of the tangent space. The generated by elements of the form. You take two tangent vector x and y, then the curvature operator is an element here. But unfortunately, so this if you just take two tangent vector at the p, then you do this. But unfortunately, this is not sufficient. So the holonomy involves global information, right? You have to do parallel transport. It's just not determined by p. So, but you can parallel transport all the curvature. Let's say zeta and the p zeta inverse, where zeta is a path from P to some other point Q in M, and XY are tangent vectors at Q. So in other words, you first you move. So this anamorphism, you first move a vector along transport to parallel travel to some other point using the curvature operator at that point, and then come back. So if you collect all these, then you will generate the algebra of the holonomy group. So the holonomy group is a global information, global counterparts of curvature, or the curvature is a local holonomy. Anyway, so this is fairly general. And then the main result about holonomy group is the result of Bourget. So Bourget holonomy theorem.
Sorry.
Yes.
Do we need the manifold to be oriented, or to be orientable, to have the holonomic group be a subgroup of SO? Yeah.
I only consider contractible loops.
Oh, okay.
Yeah. So in general, if it's not oriented, then maybe in general, if you don't consider even on the oriented manifold, you don't consider contractible loops, you may get yeah.
Okay, I see.
Okay. Other questions? So yeah, we are simplifying. So or we can assume the manifold is simply connected, just to be to avoid technicalities. So let's say, so holonomy theorem. So if Mg is complete, then we assume two things. So assume it is not locally symmetric. Meaning that, so locally symmetric means the curvature curvature tensor is covariantly zero. Okay, this is locally symmetric. So locally symmetric spaces, they were classified by Élie Cartan. And the notion of holonomy was also introduced by Cartan in the early 20th century in terms of groups. It's all classified. These are all classified. Okay. So we assume it's not locally symmetric and not locally product. So it's not locally product of two lower dimensional Riemann manifold. Then holonomy 0 Mg. Let's just now consider it's an abstract conjugacy class. So we throw away the P. Is one of the following. It's a very short list. It's first one is the full holonomy. SOM, just whole group. Second is so here it's called generic holonomy. Second one is unitary. So here the n equals m over 2. So m has to be even, and this un is a subgroup of SOM. SOM intersect GL and C. So I will explain each group, and then I will describe what it is, what is the geometry. So let's just spend some time here. So how to understand this? So we have a 2n dimensional Euclidean space. Now we can identify this with n-dimensional complex space. And then if we consider linear transformations, which is complex linear, and is preserve the inner product, then that's exactly the unitary matrix. Okay, so the holonomic group could be UN. So what does this mean? This means so the holonomic group is smaller means the parallel transport preserves more structures, right? So here, for example, in general, we can identify, so holonomic group is SOM, so we can identify the tangent space at one point with the Euclidean space with the inner product. And then you can use the parallel transport because the parallel preserve the matrix, so that means you can get the identification at every other point. So here, I can get a complex structure. They're killers. So what does this mean? So this because so this what is GL and C? This is just transformations from R to N to R to N, which commute with a matrix called J. J is the matrix 0, I, negative I, 0. It's a standard complex structure, almost complex on Cn, right? So a linear transformation, a real linear transformation, this is linear algebra, a real linear transformation is complex linear if and only if it commutes with J, it preserves I. Right. Okay, so you can spend some time. If you haven't seen this, you can spend time unwrapping this. It's not very difficult. And this object has the form A, B, negative B, A. In blocks. So how do we get a complex structure? It's from the fact that we can identify, we can define J, right? So because the holonomic group is contained in the unitary, we can identify at P, identify TPM with some CN. Okay, so that give you this identification. But then, so you get a J from TPM to TPM just by this formula. But now I can parallel transport J to any other point Q in M. So in other words, we get a J from TQM to TQM. If we connect this is P, just this is something I should understand. So this is the P, this is the Q, right? I pick a path, the zeta, connecting P to Q. I have a linear transformation here in TPM. I get a linear transformation TQ just by composing with the parallel transport along zeta. So you can do this in general. However, in general, the thing you get will depend on the choice of zeta. Right? If you change zeta to something else, then zeta prime, then you may get a different J at Q. However, if your holonomic group is contained in GL and C itself is complex linear, so then the resulting is J. Let's say that's JP and JQ. The JQ will not will be well defined. In other words, if you compose these two, you get back to a transformation at TPM, but that's complex linear, the preserved J. Okay, so this is so what it says that you will get a well-defined J by this parallel transport, and just by definition, this J will be a parallel tensor. So J itself is a orthogonal transformation of the tangent space and its parallel. So this is almost complex matrix parallel. Oh, you have a question? Did I hear a question or
I think
someone
it was
speaking?
someone on mute by mistake.
Okay, no problem. So so that means this J is an orthogonal complex structure parallel. But there's another thing that this being parallel is implies two things. One is that the Leonhardt tensor is zero. This governs the integrability of J. So i.e. the 1, 0 part of M defined by J is closed and leave bracket. And you can define a true form omega, which is G composed with J. So whenever you have an orthogonal complex structure, you can define omega. This is a true form, which is lower degenerate, non-degenerate. And then d omega is 0. And essentially, this is actually equivalent. So what is this? Maybe I think it's probably better with a local model. So just a pointwise model. So we identify a space R2n, Cn. Your remaining metric is a standard sigma I from 1 to 2n d. Let's do a complex coordinate z1 to zn, and zi equals xi plus square root minus 1 of yi. Then this is the remaining metric standard is sum of dxi squared plus dyi squared. And this j is also standard j of a partial xi equals partial yi. J of partial yi equals negative partial xi. And then the omega you get will be the standard symplectic form, dxi wedge dyi. And it is non-degenerate, so omega to the nth power over n factorial is the volume form of G. It just involves pointwise for this part, for this omega. But the point is that this for J, if you take the full covariant derivative, this has a lot of information. So one part of the information is the integrability. So this implies J is integrable. On the manifold, which means IE can find local holomorphic coordinate. It means that you can find the real coordinate x1, y1 up to xn, yn, such that J becomes standard. J satisfies this. Okay. So this is a difference between complex structure and almost complex structure and the Riemannian metric. For Riemannian metric, as we started from the beginning, you cannot make a Riemannian metric standard in the neighborhood of a point. There's a curvature obstruction, right? And if the curvature is 0, then actually you can't do this. It becomes flat. If the curvature is 0 in the neighborhood of a point, then it's you can do it. But just 0 at one point is still not enough. You have all these expansions. I wrote down the second order expansion, just curvature, but the third order expansion will involve derivative of curvature and so on. But for the complex structure, you just need this derivative, this Nyholz tensor. If it's 0, this is like the curvature of for complex structure. So if it's 0, then locally you can make this J standard. You can find coordinates such that J becomes standard, and then the Zi will be holomorphic coordinate. But you cannot use this coordinate to make a G standard. Okay. And similarly, the d omega 0, this is a symplectic form, and then this standard double theorem. So locally, you can also make it. You can also locally make it a standard. Locally, can make it standard. So that it becomes like this. So both J and omega can be independently, separately made standard. Such a metric is called Kähler metric. Okay, so we will talk about more about Kähler metric later. But I mean, I suppose you already learned complex manifolds and Kähler manifolds. Probably from a different viewpoint, you start with a complex manifold. You start with J and you try to find omega, define omega in terms of a Kähler form. But now, in terms of Riemannian geometry, that's an intrinsic characterization, just a Riemannian metric with holonomy contained in the unitary group. That's the characterization of being Kähler. Okay, so this is the second type of holonomy group. And the third type is SUN. So it's a special unitary, it's SO M intersect SL and C. Again, this N equals 2M. So in terms of GL and C, instead of GL and C, I consider SL and C. So here, it corresponds to Kähler manifold. Of course, it's a subgroup of UN. But also, because it preserves, it's determined one, it preserves, if it, at each point, CM, you identify TPM with CN. This, you can write this form, holomorphic, this complex volume form, DZ1 which to DZN. This form, you can use this to parallel transport. Because of determinant equals 1, you similarly, you see that you get a parallel complex N0 form, capital omega. Capital omega equals 0, and but N0 form, so this parallel implies that d omega is 0. This covariant encodes more information than the exterior derivative, and also it implies that its norm is constant. The omega wedge omega bar is proportional to omega to the nth power. This is this holomorphic form. This is I've seen this is a Calabi-Yau Ricci flat Kähler. So these metrics are automatically Ricci flat. So we'll again. So this is from holonomy. You see this interaction with complex geometry, and number 4 is SPN, which is a unitary 2N intersect SP 2NC. So here, M is 4N. Okay. So you identify TPM with a complex 2N dimensional. So it's R4M, the C2N. Okay, so and you have a unitary of 2n, but you have also this is a symplectic group in complex coefficients 2n by 2n. So it's like the real symplectic, but with complex values. So this will correspond to it's a subgroup of SU2n. So it's again even more special than the third type. So this is what we call hyperkiller. So it involves a killer form, a holomorphic N form, but actually it's a holomorphic. This is a holomorphic parallel. Parallel and holomorphic symplectic two form. It can also be identified with n-dimensional quaternions, and then this SPN is just the unitary transformation, which is a quaternion. Linear. So locally, let me just last a second. So locally, theta is of the form sum of dzi by dwi. Time is up. So here I will talk about 4 types. The first one is generic. The other 3 are all related to complex numbers. And now this one, the 4th one is already related to quaternions. There are 3 more. We will recap next time.